It's algebra time, and today the lesson is 10-2. We're going to be solving quadratic equations by graphing. Now that should sound familiar to you because in lesson 10-1 we graphed parabolas, which are the graphs of quadratic equations. Now today's lesson is going to be very similar to lesson 10-1. So let's go ahead and review a little bit first. Now you notice that in the notes it says a quadratic function can be written in the form y equals ax squared plus bx plus c, where a, the coefficient of x squared, can't be equal to 0. Now this is known as the standard form for a quadratic function, and we learned this before in lesson 10-1. Now if you keep on reading the notes, they should look familiar again because it says first you have to find the vertex and the additional 4 points or ordered pairs that you use to graph the parabola, just like we did in lesson 10-1, and then carefully graph the parabola. So really in 10-2, the first part of every problem is going to be exactly like the problems were in lesson 10-1. First of all, we're going to find the x-coordinate of the vertex. Remember, that's the little formula where the x-coordinate of the vertex is equal to negative b over 2a. Now, if you've forgotten that one, look back in your notes for lesson 10-1. After we find the x-coordinate for the vertex, we're going to substitute that value into our equation to find the y-coordinate for the vertex. We're going to graph the vertex, and we're going to find the additional 4 smart values for x that we're going to substitute into our quadratic function to find the y values for those 4 smart values. Those are going to give us the extra 4 points, the 4 ordered pairs, in order to graph the parabola. Now that's exactly what we did in lesson 10-1, but in today's lesson, in 10-2, we're going to go a little bit further. Now you notice further down in the notes it says quadratic solutions are also known as zeros of the equation because they are the x coordinates that have y coordinates of 0. Now what does that mean? Well, it means that when we're graphing our parabolas today, we're going to find where our parabolas intersect the x-axis. Those points of intersection where our parabola hits the x-axis are the solutions to the quadratic function. Now they're called zeros because if you recall, every single point that's sitting on the x-axis has a y-coordinate of 0. So quadratic solutions can also be known as zeros. And they also have a third name. If you notice the last line of the notes, it says quadratic solutions are also known as roots. So please remember that. Quadratic solutions are also known as zeros, are also known as roots. Okay, now let's take a look at a couple of examples. Now remember, first of all, we're just going to take a look at our equation, make sure that it's in standard form for a quadratic function, and we're going to find the vertex and the 4 smart values. Let's do that right now. Okay, in example 1, here's our quadratic function. Y equals x squared minus 7x plus 6. So the first thing we have to do is find the x-coordinate of the vertex. And remember the little formula that allows us to do that? It's negative b over 2a. So first of all, let's take a look at our standard form for our quadratic function and figure out what is the a, the b, and the c. Well, the coefficient of x squared is 1, coefficient of x is negative 7, and the constant is 6. So a equals 1, b is equal to negative 7, and c is 6. So now we can substitute and figure out what the x-coordinate of the vertex is. It's negative 7 over 2 times 1. Of course, double negative turns into a positive, and we get 7 halves, or 3 1/2, for the x-coordinate of our vertex. Now it's time to build our xy table so we can find the ordered pairs that will allow us to graph our parabola. As you can see, I've substituted the value 7 halves back into our original equation to give us 7/2 squared minus 7 times 7/2 plus 6. Now, going through and simplifying it all the way down, we find out that y is equal to negative 25/4 or negative 6 1/4. So now we have the coordinates of our vertex. It's going to be at 3.5, negative 6 1/4. All right, now that we have the vertex, we need to find the 4 other smart values for x that will allow us to graph the parabola that represents our quadratic function. And if you remember from lesson 10-1, we have to take the next 2 x values sitting to the right of the vertex and the next 2 x values sitting to the left of the vertex. Well, the vertex is sitting at an x value of 3.5. So the next 2 x values sitting to the right or bigger will be 4 and 5. And the next 2 x values sitting to the left or smaller of the vertex is going to be 3 and 2. So let's go ahead and put those values into our xy table, and let's substitute them in to find out the 4 other ordered pairs that we're going to need to graph. Well, now we have the 5 ordered pairs, the 5 points that we need in order to graph our parabola. So now do you notice, taking a look at the y column, that a parabola's y values are going to be symmetric? In other words, when you're the same distance to the right of the vertex as from the left side, you're going to have the same y value. In other words, how far is 4 in the x column from 3.5? Well, it's a distance of 1/2, and it has a y value, a y coordinate of negative 6. Now, how far is 3 in the x column from the vertex 3.5? It also is a distance of 1/2 from the vertex, and therefore it has the same y value that 4 does. It has negative 6 as its y coordinate. And how far is 5 in the x column from the vertex? It's 1.5 away from the vertex and has a y coordinate of negative 4. And what other x value is a distance of 1.5 away from the vertex? Well, 2 is, and it has a matching y coordinate of negative 4. So you can see that the x values 3 and 4 are going to have the same y coordinate, and the x values 2 and 5 will have the same y coordinate. And this creates the symmetry of the parabola. All right, now we have to go over and graph these ordered pairs. As you can see, I have graphed the 5 points on the coordinate plane, starting with the vertex and then our 4 smart x values along with their y coordinates. Now, you notice that I didn't put arrows at the ends of the curves to show that they're going to keep on going up. And that's because today, instead of just putting the arrows on the ends and calling it good, we have to find 2 more points. What? 7 points altogether? Well, in this case, yes, because as you notice, the parabola is opening up. And that means eventually it's going to hit the x-axis, isn't it? Now, where it hits the x-axis, that is going to give us the 2 x coordinates that are our solutions, or our zeros, or our roots. In other words, the answers that we're looking for. So what we have to do is we have to either continue that curve up until it hits the x-axis. Now, are you going to be able to draw your graph so perfectly that you're going to find exactly where that point is? Maybe you can get close, but it's going to be pretty tough. So here's what we need to do. We need to take a look at the original equation and remember how to factor. Remember chapter 9, factoring? Yeah, we factored polynomials that looked exactly like these functions. So let's go back to the original problem and see, maybe we can factor this and find the solutions or the zeros that way. Well, the first thing we need to remember is that when we're factoring, we have to set one side of the equation equal to 0. And since we're trying to find where our parabola hits the x-axis. Remember what's true about all the points on the x-axis? Y is equal to 0 on every point on the x-axis. So it only is logical for us in this equation to put 0 in place of y and then try to factor. Now, in case you've forgotten some of the factoring procedures, please go back to my Chapter 9 review video that has all of the different ways that we can factor polynomial equations. Now in this one, we can see that we can unfoil this equation. It's a trinomial and the coefficient of x squared is 1. So we can unfoil it nice and easily into x minus 6 times x minus 1. Now of course this means you've got a multiplication problem where either the first parentheses must be equal to 0, x minus 6 equals 0, or the second parentheses must be equal to 0, x minus 1 equals 0. And then all we have to do is isolate the variable in both of those equations. So we can see that in one equation we're going to have x equals 6 as our solution, and in the other we're going to have x equals 1. Now guess what? That means we have our two additional x coordinates. Yep, that's right. When we find the solutions to our factoring problem, those will also be the two additional x coordinates that we're going to substitute into our xy table. So let's do that right now. Okay, and since we know that these are solutions to our equation, that means they're going to have y coordinates of 0. I don't even have to plug those numbers back into the original problem. I know my y coordinate's going to be 0. So my additional 2 points that I'm going to graph will be 6, 0, and 1, 0. So let's go back to the graph and finish it off. Well, you can see that I've added the 2 additional points to our graph, 6, 0 on the right side, 1, 0 on the left side, and labeled them, of course, so everyone can see exactly where our parabola intersects the x-axis, and that means they now know the location of our solutions. Now, this actually is a kind of problem that may not happen all that often because lots of polynomial equations will not be factorable. We won't be able to use one of the techniques we learned in Chapter 9 to factor it and easily find our solutions. So we better have a way of estimating those solutions by graphing. And that's what example 2 is going to show you how to do.